All right, we're starting chapter 5 now. Chapter 5 is all about a topic called number theory. Number theory is a really interesting area of math. It's focused entirely on the natural numbers. If you remember, the natural numbers are the counting numbers, 1, 2, 3, 4, 5, and so on. At least at this introductory level, the topic of number theory doesn't venture into rational numbers like fractions. It doesn't look at irrational numbers. Sorry, let me back that up. I said it doesn't look at rational numbers. Natural numbers are examples of rational numbers, but it doesn't look at fractions, I should say. 1/2, 2/3, things like that. It also doesn't concern itself with negative numbers or irrational numbers like pi or the square root of 2. It's only looking at natural numbers. And it covers a wide variety of subjects within that context, but kind of the first major thing that we look at in number theory is the concept of what we call divisibility. And that's kind of where we're starting today. 5.1 talks about prime and composite numbers, both of which don't make any sense if you don't first understand the concept of divisibility. So I have a definition here for divisibility, but we'll talk about it also kind of on an intuitive sort of level. If a and b are natural numbers, and if there exists another natural number k, such that a is equal to b times k, then we say that a is divisible by b, and we write b, and then you see this vertical line here, a, and the way we read that is b divides a. Another way of describing the relationship between these two things, we can also say that b is a factor of a. So there's a number of different ways in number theory that we talk about how to determine whether one number is divisible by another. But the most straightforward way is to just use division. If you are asking if a is divisible by b, then what you're really doing is you're dividing a by b, and you're trying to see if a remainder shows up. If there's no remainder at all, then we would say that b divides a, or a is evenly divisible or just divisible by b. So let me illustrate that with a couple of examples. We want to check and see if the first number is divisible by the second in each of these examples right here. In other words, is 99 divisible by 3, or is 3 a factor of 99? We can check this by doing 99 divided by 3. And in chapter 4, we had to do some long division, so hopefully this is pretty fresh in your mind. 3 goes into 9 3 times. 3 times 3 is 9. We subtract and get a 0. Bring the other 9 down. And once again, 3 goes into 9 3 times, giving me a remainder of 0. So here we would say that yes, 99 is divisible by 3, because when we did the division, we got a remainder of 0. Now notice what this actually means if we try to put this back into the context of the original the original definition of divisibility. This third natural number here, k, this thing is the quotient that we got up here. So to say that 99 is divisible by 3, we can demonstrate that using long division like we did here. But then notice 99 is equal to 3, the number I was questioning if it divided 99 or not, times 33. That 33 is like the k here. Okay, so this is like a equals bk. So yes, the answer is yes, this first number is divisible by the second. And remember, we can also write that this way: 3 divides 99. Okay, let's check another example. Is 491 divisible by 25? Same method. We divide 491 by 25. Now 25 goes into 49 only once, so we get a 1 there. 1 times 25 is 25, and we subtract and get 24 in this case. Then we bring down a 1. 25 goes into 241. It goes in a total of 9 times. 9 times 25, that would be 225. Okay, and then if we subtract, what do we get here? We should get 16. Is that right? Yeah, 16. So we end up with a remainder of 16. Because there was a remainder here, that means that 25 doesn't go evenly into 491, which is the same thing as saying that 25 is not a factor of 491. Or, equivalently, we can say that 491 is not divisible by 25. One way of writing that is to write this symbolically. So it's kind of similar to using this divisible notation, this vertical bar, but then putting like a slash through it to say 25 does not divide 491. Okay? So that's just, kind of the basic idea there. Now, this concept naturally leads into something that we call factorizations, which is a major tool that we use in number theory. So first, to start with a definition, a factorization is a way of taking a natural number, like for example the number 60, and representing it as a product. So for example, 60 can be written as 6 times 10. That's a factorization of 60. 4 times 15 is also equal to 60. That's a factorization as well. We call the individual numbers that are being multiplied factors of 60. So 6 and 10, those are factors of 60. 4 and 15, those are factors of 60. Notice that each of these numbers divides 60 because of these relationships here. Factorizations can have more than 2 factors in them as well. So for example, if I wrote this 10 as 2 times 5, then one factorization of 60 is 6 times 2 times 5. I can have multiple factors showing up in a single factorization. An important consequence of this example is that factorizations are not unique in general. What I mean by that is a single natural number can have several different factorizations. So generally it doesn't make sense to say find the factorization for such and such number. More commonly we would say find a factorization because there's several options typically. So let's do an example. I want to do a couple of things here. I want to find all of the factors of 36, and then I want to express 36 using 2 different factorizations. Now, finding factors of 36 is really just a matter of coming up with numbers that can be multiplied together to make 36. So the most obvious product that makes 36 is 1 times 36. Now, I'm going to be listing these factors in a very specific way. Notice how I spread these out. The reason for that is because I'd like to get a list of factors in order from smallest to biggest, and 36 will have to be the biggest factor of 36. Numbers cannot have factors that are larger than themselves, because then you can't multiply that by another natural number and get it down to whatever that number was, 36. So this is definitely going to be the largest factor. 1 is the smallest natural number, so it has to be the smallest factor. That means all of the remaining factors are in between somewhere. Continuing on in this fashion, I have 1 as one of my factors. I'm going to count my way up from there. Is 2 a factor of 36? Well, because 36 is an even number, and by definition, even numbers are divisible by 2, yes, it has to be. But what do you multiply by 2 to make 36? 36 times 18 is 2. So 18 comes over here. And you're going to see that these factors sort of work their way towards the middle somehow. Okay, next up, is 3 a factor of 36? Yes, absolutely. 3 times 12 makes 36. Is 4 a factor of 36? Yes, it is. 4 times 9 makes 36. Is 5 a factor of 36? No, it's not. In a little bit, we're going to look at something called divisibility tests, which are tests that we can use to quickly determine whether a given number is a factor of another. And the 5's divisibility test is one you're probably already familiar with. A number is only divisible by 5 if that number ends in a 5 or a 0, which is not the case here. So 5 is not a factor. What about 6? Yes, 6 times 6 is 36. So I'm not going to write 6 twice. There's no point in that. I just need 6 to show up once as a factor. But notice I've kind of met in the middle here, and even if I did write 6 a second time, 6 and 6, there's nothing in between 6 and itself, so that indicates that I'm done. One thing I want to point out here is that the point at which I knew to stop this list is once I reached 6. And 6 is the square root of 36. Okay? Now, knowing what the square root of this number is how I know where the middle is going to be. It's how I know I can stop checking. And that's going to be important on something that we do on the next page called the Sieve of Eratosthenes. But before we get to that, I want to talk about the next part of this. We want to express 36 using two different factorizations. Well, as we worked through this, I kept saying 1 times 36 is 36, 2 times 18, 3 times 12, 4 times 9, 6 times 6. Any one of those is a valid factorization of 36. So for example, 36 can be written as 2 times 18, right? There's no problem there. Notice also 36 can be written as 2 times 2 times 9. Where did I get that from? Well, I know that 4 times 9 is equal to 36. That showed up in my list of factors here. But 4 can be broken down into its own factorization in that process. So instead of writing 4 times 9, I could have also written 2 times 2 times 9. This is the same thing. Now, when we do this, if I have repeated factors showing up in a factorization, we typically write them using exponent notation, 2 squared times 9. So this or this, these can be the two different factorizations, but as you can see, there would have been a lot of other options available there. All right, now that we've talked about divisibility and factorizations, let's get into the concept of prime numbers and composite numbers, because that's the main topic for this section. A prime number, by definition, is a natural number that has exactly 2 factors. Now, most of you are probably already familiar with the concept of prime numbers. In fact, in our last exam, there was one problem that you had to determine a truth value for, or sorry, not our last exam, the chapter 3 exam that we did. There was a problem where you were asked to determine the truth value of a compound statement, and one of the component statements was 4 is a prime number, which it is not. So I'm kind of assuming you already have some familiarity with prime numbers. However, I do want to correct a common misconception about prime numbers. Notice that my definition of a prime number does not say that a number is prime if its only factors are 1 and itself. That's what most people, I think, would say is the definition of a prime number. And the reason that's not a good definition is because that implies that the number 1 is a prime number, and it's not. The number 1, by definition, is not a prime number. In fact, it's extremely important that we don't consider 1 to be a prime number, because one of the major theorems in number theory, which we're going to talk about soon, the fundamental theorem of arithmetic is what it's called, wouldn't be true if we let 1 be a prime number. So it's actually important that we leave 1 out of the prime numbers. So a prime number is a number that has exactly 2 factors. Now, if a number has only 2 factors, then that does imply that it has 1 and itself as those 2 factors, because those are always going to be factors of a number. For example, the number 5 is a prime number. Its factors are 1 and 5, but it doesn't have any others. The number 1 only has 1 factor itself, so that's the reason it's not prime. If a number has more than 2 factors, then we call it a composite number. Up here, the number 36 had a long list of factors. There's definitely more than 2 here. So 36 is a composite number, not a prime number. Okay? Prime numbers are extremely important to number theory. They're kind of like the central object of study, in a sense, in number theory. And knowing the prime numbers is extremely important for a number of applications. We might talk about some of those later. So being able to identify whether a number is prime or not is an important thing to be able to do. Now, there's a number of different ways of going about this, but one historical method is something called the Sieve of Eratosthenes. Eratosthenes was an ancient Greek mathematician, among other things. He did a lot more than just math, but he devised this method, and we're going to show in the next example how it's used. So right up here, okay. What we'd like to do is use this technique that we're going to illustrate here called the Sieve of Eratosthenes to identify all of the prime numbers from 1 to 100. Now, what we're going to do is start by just crossing off numbers that are not prime. And based on the discussion that we just had, the number 1 is not a prime number. Next thing I want to do is go to the number 2. 2 is a prime number. It's very easy to list the factors of 2. The factors of 2 are 1 and 2. There's no other option. So 2 is definitely a prime number. Now what I want to do is notice something that happens if I count by a number. Let me go down here. So we just said 2 is prime. But what happens if I count by 2s? 2, 4, 6, 8, 10, and so on. If I'm counting by 2s, then what that automatically does is it generates a list of numbers, all of which have 2 as a factor. That's what counting by 2s does. It generates all of these numbers that have 2 as a factor. So that means the number 4, for example, has 1, 4, and 2 as its factors. 6, in addition to 1 and 6, also has 2 as one of its factors. It also has 3, but that's kind of beyond the point. So every number after 2 is guaranteed to have at least 3 factors, because in addition to 1 in itself, we also know that 2 will be a factor. That means every single number in this list after 2 has to be composite. So I'm going to count by 2s and cross off everything after the number 2 in that process. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Now you may notice as you kind of go through this, that numbers, we're basically crossing off all of the even numbers except for 2, and those are all arranged in columns. So I might make this a little bit faster on myself if I just kind of go like this, because here I'm accounting for all of those even numbers that I would have counted in this process here. Okay, boom, 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 boom. Now if you've noticed, I've just eliminated about half of my list. This is a process of elimination kind of procedure, and I've just eliminated half of the numbers here. So that's done away with a lot of candidates. What I'm going to do is move on to the next number that has not been circled or crossed out, which would be the number 3, and automatically it needs to be prime, because if it is not, it would have been crossed out in this process. 3 is a prime number. Its only factors are 1 and 3. Now if I count by 3s, 3, 6, 9, 12, etc., then by the way that we're doing this, every single number in this list after the number 3, well, including the number 3, I guess, has 3 as a factor. 6 is divisible by 3. 9 is divisible by 3, so is 12. And because those numbers are also divisible by 1 in themselves, they have more than 2 factors. They are all composite. So I do the same thing. I count by 3s and I cross everything off after the number 3 that I encounter. Now, because I've already crossed off a bunch of numbers, you're going to see that about half of the numbers that we would encounter counting by 3s are already crossed off. So we don't, we just kind of move past those. 3, 6 is already crossed off. 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, 39, 42, 45, excuse me, 48, 51, 54, 57, 60, 63, 66, that one's not clearly crossed off, but we did cross that off before. 69 is a composite. 72, 75, 78, 81, 84, 87, 90, almost there, 93, 96, and 99. And that's as far as I can go from the numbers 1 through 100. So we crossed off several more numbers in that process, all of which are now known to be prime numbers. Okay? Then I would move on to the next number in the list and repeat this process. 4 would be the next number, but it's crossed off. So we know it's composite. We're not going to count by 4s. We're just going to skip past that to 5. 5 which we already stated previously is a prime number. I repeat this process here. Now I'm gonna do this until we're done, but it's important to know when to stop, because as you can see, if I'm gonna do this all the way down to 100, you can see it's gonna take a long time. However, I want to remind you of something that we saw in this example here. I knew to stop listing these factors when I got to the square root of 36. And that's because as I'm finding factors that are smaller than 6, in that process I'm automatically filling in the factors that are also to the right of 6. Remember, 1 times 36. Because I knew 1 was a factor, 36 goes with it, and so I kind of get that one for free. And then 2 is a factor of 36, but that's multiplied by 18 to make 36, so I automatically get this 18. So if I only worry about the numbers that come before the square root of 36, then I know that the rest will be accounted for automatically. It's the same concept here. I'm going from 1 to 100. I don't need to bother checking any of the numbers that are greater than the square root of 100. I can just work my way up to the square root of 100, which is 10, and then all of the numbers beyond that will be accounted for already. So that means we don't have to spend forever on this one problem. Let's count by fives. The nice thing about fives is if you count by fives, 5, 10, 15, 20, 25, 30, and so on, all of those numbers are arranged in columns as well. 5, 15, 25, 35, 55, 65, 75, 95. Need to cross all of those off. These numbers, 10 through 100, are all even, and so we already crossed those off when we were, make that one a little bit more pronounced, when we were counting by twos. Now notice, again, like I said, we don't continue past 10, but I've already crossed off 8, 9, and 10 in this list, which means we don't even need to bother with those. 7 is the last number we need to worry about. So 7 is prime, its only factors are 1 and 7. Now we start counting by 7s. 7, 14 is accounted for, so is 21, and 28, and 35. You're looking at this and you might be thinking, is there going to be anything that's not already crossed off? 42 is crossed off, 49 is not, so we're going to include 49. And then 56, and then 63. Plus 7 would be 70. 77, got to cross that off. 84 would be next. 91 is not prime. And then 91 plus 7 is 98. That accounts for everything else. So now we know that we're done, and now we can go and find any numbers that are not crossed off and circle those. Those will be the prime numbers that are left. So we finished off this first row. 11 is prime, so it's 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, 97. Did I miss any? I'm going to make sure I didn't miss any. I think everything has been accounted for now. So one thing there's a couple of things I want to look at actually here. First of all, notice that after the number 2, all prime numbers are odd numbers. So 2 is the only even prime number, and that makes perfect sense because, again, down here, we said that when you count by twos, you're listing all of the even numbers, all of the positive ones anyways. And because they're even, they're divisible by 2, so they cannot be prime except for the number 2. So that's one thing. All prime numbers are odd numbers except for the number 2. In addition to that, none of the prime numbers except for 5 itself have a 5 in the ones place because, again, all of those will be divisible by 5. So what does this mean for us? Well, there's only 4 single-digit prime numbers. And if we look at prime numbers that have more than just one digit, we can narrow them down into one of 4 categories. Ones that have a 1 in the ones place, a 3, a 7, and a 9. Those are the only possibilities for multi-digit prime numbers. Kind of interesting. That narrows things down by a lot. In addition to that, there's a couple of numbers that are oftentimes mistaken for prime but are also composite, namely 51 and 91. When you start working with prime numbers and composite numbers a lot, you start to kind of get a little bit of a feel for whether a number looks prime or not. And 51 and 91 are numbers that kind of look like they should be prime, but they're really not. 51 is 3 times 17, for example, and I believe 91, I think, is 7 times 13. So these numbers are not prime, even though they may kind of look like a prime number. That's going to be it for this video. We'll keep going in the next.